Good morning, students. Sir, is it audible?
No, వినిపిస్తుంది మేడం.
Okay. మా స్క్రీన్ కనిపిస్తుందా సిఆర్?
మేడం కనిపిస్తుంది మేడం.
ఓకే ఓకే. So in the last class we had completed the furnaces, what are different types of furnaces are there. So in this class we will learn about what is metal casting, and in the last class we will learn about the gating systems also. What are the different types of gating system, pressurized and unpressurized gating system. So how it is to be get arranged. So what is the type of material is to be get poured, and what are the types of defects are to be get occurred when a gating system is not correctly placed. So, what type of gating systems, how it is to get placed, whether it is in a top gate or a bottom gate or a medium center parting line gate. So, how it is to be. So, it depends on the metal what you are going to be chosen. So, the gating system is to be get chosen, and as well as what is the ratio you are going to be given. So, weigh the size of the choke or size of the area of the runner or area of the in gate. So, which is to be get varied. So, depends on the metal that is to be get varied. So if you are going to be taking a pressurized gating system, so what are the advantages and what are the disadvantages? So if you are taking an unpressurized system, what are the advantages and what are the disadvantages? So this we had learned in the last class. So in this class, we will learn about what is a metal casting, design, materials, and economics. Right. So in the introduction, we will explain that. So in an introduction, it explains that a successfully casting practice requires the proper control of a large number of variables, characteristics of the metals or alloys cast, method of casting, mold die materials, mold die design, and various process parameters. So if you want to get a successful casting product, what is the things is to be get followed? So what are the characteristics to be get followed for it? So where to be get control to, when we have to get a correct casting product. So you have to get control at a core sand, or we have to get control at a gating or a design mold design. So what type of design we are going to be used, whether it is a permanent design or it is a some other type of pattern. So the second point is the flow of the molten metal in the mold cavities. The gating systems, the rate of the cooling and the gases evolved all influence the quality of a system, all the influence the quality of a casting. So it depends on the flow of the molten metal only. The characteristics of the piece is to be get determined, because if the flow of the molten metal is not in a correct manner, so what type of things, what type of properties are to be get existed in a product. So whether it is having a good strength or a good toughness, or it can be have a good resistivity or any other thing. So what are the properties are to be get happen for each and every product. So how it is to be get determined. So how what type of flow pattern is to be get arranged. So when the flow pattern is arranged correctly, but what is the rate of cooling? So at what temperature you are pouring the molten metal? So whether the molten metal is to be get cooled or it is at the same temperature. So when the molten metal is to be get carried over to the sprue and runner and the gates, whether the same it is going to be maintaining, or any high temperature is to be get evolved for it. So we have to see it is at each and every stage. So what are the gases evolved? So for this only we are going to be arranged what are the different types of vent holes. So how the vent holes are to be get arranged so that any gases are there in your product, it can be get removed. So how it is to be get arranged. So this chapter describes the general design considerations and guidelines of the metal casting and presents the suggestions for the avoiding defects. So what it explains is when you follow each and every part, each and every design, so the defects which are going to be getting for your product, it can be get reduced. So to reduce the casting defects, we have to follow some different types of rules that is to be get considered, right? So next one, design considerations in the casting. Design the part so that the shape is cast easily. So we have to design the part in such a manner that the shape is to be get in the easiest way. The shape cannot be get break at a corners or any other thing. It must not be have any cracks or any other. It must not be having any holes. So if to reduce this one, so what type of shape you are going to be get selected. So already you had learned how what type of shapes to be get used in a casting in your first unit, first or second unit, I think. So that type of rules are to be get followed while you are going to be designing some product. So select a casting process and material suitable for the part, size, mechanical properties, and etc. So what type of mechanical properties it is going to be having. So select a casting process and material suitable for the part size. So depends on the part, depends on the pattern, depends on the size of the piece which you want to get out. So depends on the mechanical properties, what type of process is to be get followed. If you are going to follow a certain process, a certain metal, but it is not suitable for a certain type of casting process, so we can't get a good properties. So what type of metal you are going to be chosen and what type of casting process is to be get needed. So third point, locate the parting line of the mold in the part. So locate the parting line. So when you are going to be doing certain coconut rack, how you are going to be placed. So locate and design the gates to allow uniform feeding of the mold cavity with a molten metal. So locate and design the gates. So in the last class we have learned about what are the types of gates. So how it is to be get located. So what type of molten metal where you are going to be locating. So if you are using a top gate, so what are the advantages and what are the disadvantages? If you are using a bottom gate, advantages and disadvantages. So we must require a uniform feeding. So I already told you in the last class that it must not be having a high velocity. It must not be have a low velocity. It must be contain only medium thing. If it is having a high velocity, what it means, we are the certain amount of molten metal cannot be bind itself. Yes or not? So when it is having a very low velocity, so the starting pumped molten metal, it is to be get cooling, and after pumping molten metal, it cannot be get up to that point. So some type of defects are to be get erased. So when the molten metal is sent to the total part mold system, so we have to maintain a certain temperature. So we have to maintain a certain uniform diameter, so that the total molten metal can be get solidified at a certain time only, right? So the fifth point, select an appropriate runner geometry for the system. So we have to select an appropriate runner geometry. So from the runner only, the molten metal is flowing over towards the ingates. So what is the diameter of your runner? So how it is to be get selected. So locate the mold features such as a sprue, screens, and risers as appropriate. So where you are going to placing a sprue, where we are going to placing the riser. So what is the use of the screw and what is the use of the riser? So what are the different tools to be get used to get your perfect molding part? So seventh point, make sure the proper controls and good practices are in the place. So we have to be get controlled. So when you are placing a screw, it must be placed in a correct manner. It must not be loosed. It must be somewhat tight, because the screw cannot be having continuously. You are placing a screw and you are putting a green sand. I think it is a sand casting. You are placing the screw and you are putting a green sand. And after ramming, what you are doing? You are removing the screw. So the whatever the dimension, whatever the area which you have made to while using the screw, it must be correct. Now, after removing the screw also, it cannot be get disturbed. So we have to control each and everything. So this comes only when you are having some type of experience, right? So next one, design considerations in the casting, design of the cast parts. So corners, angles, and section thickness. So in the last class, in the previous first unit, I think so, we have learned about the corners cannot be get encouraged. The angles are not to be get encouraged. The section thickness, the thickness must be somewhat medium. It must not be very, very thin. So sharp corners cannot must not be get encouraged. So whatever things are to be get used, so that is to be get considered. So design considerations in a casting, design of a cast parts. So the first one, A section, poor and a good. So this is the A part and this is a B part. So in an A part, you are going to be doing a correct shape of the piece. But in a in this section, this is the poor part and this is a good part. Because in the first part, it explains that it is having a sharp corners. So when you are doing some type of machining process, it can be a trick. So we have to be used some type of a smooth curves, fillets, right? So in a B part, the first diagram is poor and the second diagram is perfect. Because in the B part, the first diagram explains that it is having a sharp corners and the down part explains that it is having a very smooth corners. Right. So suggested design modifications to avoid the defects in the castings. Note that the sharp corners are avoided to reduce the stress concentration. So whatever the stress, what are the sharp corners which are going to be designed, it is to be get avoided. Right. So next one, design considerations in the casting, design of a cast parts. So sections changes in casting should be blended smoothly into each other. Location of the largest circle that can be inscribed in a particular region is critical so far as the shrinkage cavities are concerned. So because the cooling rate in regions with large circles is lower, they are called hotspots. So these regions can develop shrinkage cavities and porosity. So it is explaining about this all. It is explaining this all. The first thing, see the first diagram, A point. So in an A point, it is having a very sharp corners. Just avoid the sharp corners. So just avoid the sharp corners and make a fillet type of corners, and which you can see in a B part, and in the C part, in a C diagram, the shrinkage cavity is to get occurred. It is a poor. It is a poor because when you are going to prepare the angular sections, so you have to be put some type of pressure. So it is have some type of shrinkage is to be get occurred at the corners. Right, it is not a very smooth, and the in a downward direction, it is good. It is a good under the sea. So it explains that you are having a fillet type of diagrams. And in a D part, it is in a D diagram. It is of very poor because it is having in a X direction. So in an X direction, when you are getting when the solidification is to be get done, some type of material is to be get stick on in the middle only. It cannot be get solidified. So it is nothing but one type of poor defects which are going to be get occurred. So the second, the below diagram explains that one type of angular thing must be at one direction, the second type of angular thing is in the another direction. Right, this is the good part. So comes to the E diagram. In an E diagram, we can see the top diagram, which is a core. But compared to this one, this is the bottom one is a correct. The bottom one is a correct because in a E point, it is having the core at the certain point, but in a bottom, it is in a Y direction, which is having somewhat the smooth. So examples of the designs showing the importance of the maintaining uniform cross sections in a casting to avoid the hot spots and a shrinkage cavities. Okay, so for this type of diagrams only, they are explaining in this slide. So it explains that design considerations in the casting, design of the cast parts. So the first point explains that the sections change, the section changes in the casting should be blended smoothly into each other. Location of the largest circle that can be inscribed in a particular region is critical so far as the shrinkage cavities are concerned. So we have to see that no shrinkage is to be get occurred in a total part of piece. So because the cooling rate in regions with large circles is lower, they are called the hotspots. So when you are getting some type of circles, bubbles, so that is nothing but one type of defects only. So these regions can develop the shrinkage cavities and the porosity. So the cavities at the hotspots can be eliminated by using a small course. By using a small course, it can be get eliminated. So it is important to maintain as much as possible uniform cross sections and wall thickness throughout the casting to avoid or minimize the shrinkage cavities. So metal chills in the mold can eliminate or minimize the hotspots. So metal chills in the mold can be get eliminate or minimize the hotspots. So this is the thing which is to be get eliminated. So examples of the design showing the importance of the maintaining the uniform cross sections in castings to avoid the hot spots and the shrinkage cavities. So in the first diagram, so the first diagram is poor, and in the A part is poor and the B part is right. it can be used, this type of thing, because when you are going to be designing this angular sections, because when you are going to designing the angular section, some type of shrinkage is to be get occurred. So it is better to design in a B part, B section. So comes to the C. Comes to the C, it is a very angular part. It is a 90 degrees angle. So there in a center at a corner, it is to be having a shrinkage cavity. So it is poor, and the C, the second bit is good. So the comes to the D point. So in the last page, I have told you the first thing is poor, and the second is good. And comes to the E part, it is having a core in the red part, so it is poor, and a Y is correct, right? So this slides, it explains that which type of parts can be accepted, which type of parts can be rejected. So that explains this part. So when you are going to be designing in such a type of angular sections or certain type of sharp corners or any other very small thicknesses. So what type of defects you are going to be getting? So when you are placing a very small thickness, whether it is to be get accepted or not. So when it is having a very sharp corners, it is accepted or not. So what type of thing? So this is the design considerations in the casting. So design of the cast parts. So first figure 12.3, it explains that examples of the design modifications to avoid the shrinkage cavities in castings. So if you want to avoid the shrinkage cavities in the castings, so which is to be get used. So see in this diagram, A diagram. So in an A diagram, so in an A diagram, it is going to be having a very sharp corner, and it is having a very thickness, a very less thickness. So it is very having a very it is a poor quantity. The distance of each and everything is also very poor. So you are having a very sharp corners at this point. So at this point, you are having a very sharp corners. So it is better to avoid this one. So in the second, in an A bit, it is telling a good. It explains that the thickness of the base to this one, the top, it is very small. The thickness is very small, and it is good. Okay. So comes to the B. Comes to the B. It explains that the first diagram is poor, and the second diagram is good. So comes to the C, it explains that uh, the first one is poor. So it is having a shrinkage cavity is going to be occurred at this point, and you are going to placing a two parts risers. And the C point, it explains that it is a good. It is a good. We are having a riser at this point. So shrinkage cavity. So in the second, this 12.3 explains that examples of a design modifications to avoid the shrinkage castings in the cavities in the castings. So 12.4 explains that the use of the metal padding chills to increase the rate of cooling in thick regions in a casting to avoid the shrinkage cavities. So this is the 12.4 explains. So shrinkage cavity. So the first one is poor, so which is having a shrinkage, and the second one is right because it is having a metal padding chill up to the end. But in this one, only the top it is going to be having. So in this one, the 12.4, the left side is poor and the right side is good. So the next, so the design considerations in a casting, design of the cast parts. So it explains that what type of defects we are going to be getting, how it is to be get avoided. So the first one is flat areas. Large flat areas, plain surfaces should be avoided since they may warp during the cooling because of temperature gradients, or they develop the poor surface finish because of uneven flow of the metal during the pouring. So to resolve this one, can break up flat surfaces with a staggered drips. To avoid this one, it is to be get attached with any other flat surfaces, right? So the next is shrinkages. So shrinkages, it explains that pattern dimensions also should allow for shrinkage of the metal during the solidification and the cooling. So allowances for the shrinkage known as a pattern maker shrinkage allowances usually range from about 10 to 20 mm per meter, 10 to 20 mm per meter. So the allowances for the shrinkage, also known as pattern maker shrinkage allowances. So it is ranges from 10 to 20 mm per meter. So this table 12.1. So this is a table 12.1. It explains the shrinkage allowances for the casting in the sand walls. So this you can observe here, students. The first one, the gray casting. What is shrinkage allowances can be get accepted. So in this, the gray cast iron, it is a 0.83 to 1.3. In a white cast iron, it is 2.1. In a malleable cast iron, it is 0.78 to 1. So in a aluminium alloys, it is 1.3. Magnesium alloys, it is 1.3. Yellow brass, 1.3 to 1.6. Phosphorus bronze, it is 1.0 to 1.6. So aluminum bronze, it is 2.1. High manganese steel, it is 2.6. So these are the metals which are going to be having, and what is the temporary percentages to be get accepted. So this is the normally shrinkage allowances for the some type of metals in a sand molds. Okay, so you can see another diagram in this. Design considerations in the casting, design of the cast parts. So the first one is interior reinforcement ribs. So the figure adding ribs to flat region decreases wrapping and increases stiffness against bending moments. Against bending moments. So when it is having a bending moments, how it is to be get reinforced. So what are the other adjustments are to be get taken. So when it is having a very angular, when it is having a very small thicknesses, so how it is to be get the stress, and how it is, how the force is to be get applied for it, the pressure is to be get applied when certain ramming is to be get done. So what is the thickness of that? So it describes when this type of diagrams can be used, can be made only by unconventional machining process, because by using a conventional machining process we can't make it perfectly. So most of the times they will use the unconventional machining process to complete these type of diagrams here, because in the inner part you can also see here, in the inner part it cannot be taken easily. So here the typical pattern makers shrinkage of various metals. So metal, the percentage and inches per feet. So aluminium, if you take it for an aluminium, the percentage is 1 to 1.3. If you are take for an brass, it is 1.5. If you take for a magnesium, it is 1 to 1.3. If you take for an cast iron, 0.8 to 1.0, steel 1.5 to 2.0. So these are the metals. For this metal, this type of percentages to be get accepted. So next one. So it totally explains about when you are going to be casting, casting is to be get done, what is to be get considered. So when you are doing some type of angular shapes or any other, so when you are attaching any other motor metal on it, so how it is to be get considered. So the draft, a smaller draft tapper typically is provided in a sand mold pattern to enable removal of the pattern without damaging the mold. Drafts generally range from 5 to 15 mm per meter. The drafts generally range from 5 to 15 mm per meter. And depending on the quality of the pattern, draft angles usually range from 0.5 degrees to 2 degrees. So draft a smaller draft tapper when you're going to be using a tapper part. So typically is provided in a sand mound pattern to enable removal of the pattern without damaging the mold. So without damaging the mold, how it is to be get taken. So, drafts generally range from 5 to 15 mm per meter. So depending on the quality of the pattern, draft angles usually ranges from 0.5 degrees to 2 degrees. So dimension tolerances should be as wide as possible within the limits of a good part performance. Otherwise, the cost of the casting increases in commercial practice. Clear. So when you are want to making the dimension tolerances, how it is to be get maintained. Tolerances, shrinkage tolerances, or any other tolerances. So clear, what how it is to maintain. So what type of upper limit and what type of lower limit is to be get considered. So tolerances should be as wide as possible within the limits of the good part performance. Otherwise, the cost of the casting increases in commercial practices. Tolerances are usually in the range of plus or minus 0.8 mm for small castings. So when you are taking for a small casting, it is plus or minus 0.8 mm. So when you are taking for a large castings, tolerances may be plus or minus 6 mm. Okay. So lettering and markings, when some lettering and markings is to be get done. So it is a common practice to include some part of the part identification such as lettering or corporate logos in the castings. These features can be sunk into the casting or protrude from the surface. So it is to be done on the surfaces only. It is to be done on the surfaces, lettering and the marking. Um, so it is a common practice where when some big companies, they want means for each and every product it is to be get manufactured from their company, it must have some logos, some letters, some identification. So that is a common thing which is to be get. So these features can be sunk in the casting or protrude from the surface only. Okay. So the machining and finishing operations should be taken into account. For example, a hole to be get drilled should be on a flat surface, not a curved one. Better yet, should incorporate a small dimple as a starting point. So features to be used for clamping when machining. So features to be get used when clamping when machining. So machining and a finishing process. So how the machining is to be done and how the finishing operations can be get performed. So it should be taken into account. For example, a hole can be get drilled should be on a flat surface. So on a flat surface, it can be get drilled easily, but on a curved one, it cannot be get done. Yes or not? Because it can be having some type of shrinkage cavities on workpiece when you are going to be happen, or it can be occurred any cracks on the piece. So better edge should incorporate a simple dimple at a starting point only. So when you are going to be manufacturing a workpiece, it's better to make a starting a small hole or a small identification. So it is starting only. So features to be used for clamping when machining. Features to be used when clamping for clamping when machining. Okay. So the next design considerations in the casting, selecting the casting process. So casting process selection cannot be separated from the discussion of the economies. However, tables 11.1 and 11.2 explains, wait. So in the next tables, we will learn about what are the advantages and limitations of the casting process that have an impact on the casting design. I will show the tables of the thing. Okay, students, I will show it in the next class. The tables it is missing in this one. I will show in the next class. So is it clear, students? Any doubts you're having?